research as I possibly could, because I wasn't the girl who was, looking up at the stars when I was really young and thinking, oh, I wonder what's out there. And I just wasn't a space kid. I didn't watch Star Wars or Star Trek or any of that. I just kind of fell into it very accidentally. But yeah, that's how I ended up at Astro. But I guess then comes the Galileo Project, which I think is a fun story. So that was my senior spring. And, so last semester, nearing the end, it's in sight. And I have a professor who I'm very close with, he was an academic, very important academic mentor for me. And he approached me and he said, I have an opportunity to do an independent study, which basically just meant, I get to control the terms of the project and I can do it at my own pace and then, produce some kind of written report at the end summarizing everything I've learned. And he approaches me and he says, oh, would you like to do an independent study on exotic solar system ices? And I'm thinking, where did this come from? I took planetary science with him, but I didn't have too much experience with chemistry or anything. But I was like, okay, I really look up to him and I would love to work with him, on a independent study and, really improve my ability to do science by myself and not just, doing problem sets and taking
Was
exams.
This in line with what you were doing in the undercourse as the observational astronomy? Was it related to that, or was it a different subset of astronomy?
I think it was a different subset. So it definitely leaned more like planetary science. So I was looking more at something called spectroscopy of ices. So looking at what they look like in that area of science. So I wasn't looking at like stars and galaxies and whatnot. It was more at like
Close in
objects.
range?
Yeah. So I guess it was like comets and asteroids is really kind of where it falls. So I started doing this independent study and my professor is like, okay, and actually in a different class with this professor, he starts talking about the Galileo Project and how it was kind of sparked by this object that was observed in 2017 called Oumuamua. I'm not sure. Have you heard of?
I have.
Yes.
Yes.
Yeah. So this object that flew by, interstellar object, that they didn't really know what it was. There's different hypotheses out there, nitrogen iceberg, hydrogen iceberg. And then there's this other hypothesis, which was presented by Dr. Avi Loeb at Harvard. And he claimed that maybe this object could be a remnant of, an extraterrestrial civilization, like basically space junk that is from another system that flew by our solar system and we observed it. Just because there are a couple properties that were just like weird about it.
What properties?
Yeah, I think there was non-gravitational acceleration when it ran around the sun. So it basically had a kick, I believe, in its speed. But
So as it was going around the sun or near the sun, you would expect it to accelerate due to the gravity, but it was accelerating, but it was accelerating faster than what you would expect. Is that
yeah, exactly. So it was almost like a kick, I think, to my understanding from what I recall of that. And it had no tail, cometary tail. So when you see a comet, usually its tail that's coming from as it gets closer to the sun, it's heating up and the ice starts to turn into gas through a process called sublimation. And there's no tail. So I was like, okay, well, we can't call this thing a comet because it doesn't have a tail. And it experiences kind of non-gravitational acceleration. So what could this thing be? And I think Avi got a lot of criticism for that hypothesis, but it's like we didn't have enough data to say if it was true or not. But anyway, so then that's basically what my research was without me knowing. It was related to the Galileo Project and one of their other branches, which is, looking at interstellar objects and their origins.
Okay.
So that's how I fell into it. It's a long story.
So your professor at Wellesley brought you into a project studying ice fragments within the solar system, which typically gets classified as comets or
or asteroids.
Yeah. And in this particular case, there was an interesting comet or asteroid or something else that everyone assumed was a comet, but it didn't have the characteristic.
Exactly.
Yeah, the characteristics of one, and performed some interesting things. So that was your introduction to it. Very cool.
Yes.
So that was your introduction to what it was.
Yes.
What did you think when you heard that? Was this something you're like, okay, yeah, that makes sense, or did you kind of have to step back and kind of reevaluate what you were being offered in a sense to study?
Yeah, I mean, I think I basically signed up to do the independent study so early that when I actually found out what it was about, it was pretty much too late for me to make any other decision. But I was fine with that. I was like, this is my senior spring. Like, I'm not going to get these chances to engage in this kind of research again. And even so, the research is valuable for many other applications. So basically what I was doing, and actually there's a paper from the Galileo Project that's coming out this spring. I don't know exactly when about this, but it was accepted. So that's exciting. I'm one of the co-authors on it, so that's cool. Thank you. But it's about, physical considerations that we would take if we would want to rendezvous with a interstellar object that was coming by. So the first question is, well, how do you determine that something is weird? So, if we could look at something using spectroscopy and say, oh, well, this is made of water and carbon and, hydrogen. Okay, well, that's probably not super interesting to us. We've seen things like this. It's probably just, a comet.
Sure.
So in that case, we wouldn't want to rendezvous. But in the case of the Oumuamua, what would have been awesome is if we had something saying, hey, this thing is weird for XYZ reason. Let's go out to it and investigate it. So we'd send something out there to fly by with it, rendezvous, maybe get some close-up imagery or take some other measurements of the object, and then we could better understand what the thing was. Because that's the thing about Oumuamua, we just didn't have enough information to, say what it was, or we didn't have, modeling that would allow us to come to a definite conclusion. So it kind of just remains this open question, and it flew away from us. So we're not ever going to catch up to it again.
Why is it so difficult to either find or to rendezvous with these?
I mean, they're flying at just really insanely high speeds. So I think, I don't know the exact speeds. Part of me thinks maybe 10 kilometers a second. But
so it's kind of like a bullet coming into the solar system from somewhere else.
It's flying so fast.
Okay, so it's on a totally different scale of the planets, things of that nature.
Right, it's not in this nice orbit, this stable orbit around the sun, everything's moving. It's coming in, and maybe it flies by Jupiter, and it might, Jupiter has a large mass, so it's going to change, it's going to influence it with gravity, and it might change trajectories and everything. So it's really hard to, we have good models for how, when things are coming in, where to predict that they're going to end up. But, in terms of it's hard to pinpoint where something's going in, have, something out in space that's going to fly to it, just because it's moving so fast. It just costs a lot of money. So,
but we've done that with other comets, correct?
Yeah, or there was, I think, recently something demonstrated. It was for more national. I guess you would call it national security. I don't know what the official term would be, but a group kind of flew out a probe or something of nature to smash into an asteroid to change its direction, of course. So we want to smash into the thing, unless it's coming at us, then we definitely want to do that. But this would more just be like a flyby, let's get some imagery or maybe close-up spectroscopy or other things of that nature about this object, just so we can say more, because we just don't have enough data to determine.
And they're moving so fast, we would either need to have things out there ready to intercept, or we'd have to detect it at an early enough position to send something out.
Exactly. So it's kind of like that. It's a give and take. So you want to have maybe some facilities on Earth that are, looking like the Vera C. Rubin Observatory, that are looking for these objects in the sky. And maybe once you see one and observe one, you're like, okay, well, we maybe have this some kind of probe or something out in space in a stable orbit waiting for a green light. And it's like, okay, I'm waiting for this on Earth observatory to signal that this thing is weird. Once that happens, we can say, okay, go ahead, fly. So it's really hard to determine that, certain things about an object when it's so far away. So that's why we lean to spectroscopy, because it is one of those things that we can see. And that basically just...
At distance.
Yeah, exactly. It's something you can measure with distance, and it just gives you signatures of different wavelengths, and you can see absorption and emission lines, and then determine, based on our research in labs, those are consistent usually, whether you observe them on Earth or out in space, so you can see, okay, we know if there's a dip here, this means that this is the composition. So I think they're starting to do that now with JWST and exoplanet atmospheres.
James Webb.
So James Webb Space Telescope, yes. So
very good.
Yeah.
That's fascinating. What are we using to detect these smaller objects before they get in the solar system, if we can? Do we have that capability yet, or do we have to wait for them to get closer and then we find them and we can figure out they came from external to our solar system after the fact?
Yeah, so I actually don't know too much about that myself, but I know, for instance, another aspect of the Galileo Project, another branch still working towards that interstellar object origins kind of research goal, is they have an expedition going out to Papua New Guinea that's looking to retrieve fragments of an interstellar object. So that, for instance, they were able to track that trajectory and then based on its trajectory determine, okay, this did not come from our solar system. So I think that's just like theoretical physics, calculating trajectories. But at that point, I think you have to wait till it's close enough that we can, resolve it and see it in the sky with our telescopes. And I mean, telescopes are getting better every year. So as we get more and more telescopes or even things out into space, you don't have to fight the atmosphere when you're observing, you're not inhibited by a cloudy night per se. So, as even more as like private space companies come into the sphere, I don't know how open they are with their data, but as we get more as these technologies develop and as we just get simply more of them, there'll be more eyes on the sky. So
well, one of the things I understand that for the object that is in the ocean that the Galileo Project or Dr. Avi Loeb was talking about going and investigating, they had a supposition about that particular object, and they were waiting for additional data from classified systems to confirm whether or not the trajectory was truly extrasolar.
Right.
That's my understanding. Can you speak to that at all?
Yeah, I wish I could speak more to it. That's the one branch that I haven't really, been involved with too much. But I think they were able to, there's some calculation that they were doing where they were just trying to pinpoint like where exactly it was. And I think they were waiting on information there because the government had tracked it because, if something's flying into the Earth, the government's on it. So since it was the ocean, it wasn't a threat or anything. But they were trying to, pinpoint that location. And I think they were waiting for more data for that front. But I think they were able to make progress with their calculations or something to improve the resolution. But that's as far as I know.
Yeah.
I think I remember them being a little bit frustrated, I guess, with the fact that they were trying to do this for science and, the government wasn't necessarily cooperating, but they have their reasons and we have ours. So.
Yeah. It's a trend that I've seen, and it's not necessarily a negative thing. We put a lot of money and effort into developing weapons and systems and sensors within the government. And those things typically, we like to hide how well they work, obviously, from our adversaries.
Exactly, yeah.
And so, this is, it doesn't necessarily mean the information that is captured is classified, but just the fact that you could detect something at a particular range or know the size or the resolution. And that's what we see a lot in the unidentified anomalous phenomenon area. When I was flying, we were seeing objects on the radar. The objects themselves weren't necessarily classified. At least no one told me that. But the systems we were capturing it on, such as the radars and everything else, were classified. In the Galileo Project now, I believe one of their taglines is the sky is not classified.
Yeah.
But maybe you can talk about what their goals are now and how they're trying to essentially gather data outside the realm of government oversight.
Sure. So at a high level, I would say the goal of the Galileo Project is to bring the search for signatures of extraterrestrial civilizations to a standard where there is rigorous scientific investigation and there are, credible instruments and people behind these discoveries, basically bringing science to the conversation. Because I think that's something that's been perhaps missing in recent history. So, I mean...
Why do you think that is?
I wish I knew. It's hard for me to imagine that because I think, most people I talk to, even friends, colleagues, family, are so interested in the subject and they're like, yeah, totally, like we should look at something. We don't understand it. And I think the only thing that I can justify this with is just that it makes people and authority uncomfortable. So I guess what I mean by that is, and I guess we've seen this kind of in different cases in a little bit different ways. So with astronomy, there is like dark matter and dark energy. This has, been shown to make up a vast majority of our universe. But scientists really don't know what's going on with it. That's why we call it dark matter and dark energy, because we're like, oh, it's dark. We don't know what it is. So there's a whole study about like trying to figure out what exactly that is. And for some reason, that is fine to do. When we don't understand something, okay, let's look into it. But when it comes to UAP, that same logic isn't applied. And I think this kind of has to play into what I might foresee as a paradigm shift occurring in the future if we would make more progress. So what I mean by that, A paradigm is basically a belief system or theory that provides like a unifying explanation for a set of phenomena or, in some field. So a set of phenomena in some field. And it usually also suggests methods for which ideas are tested or knowledge is advanced. So paradigms, are upheld in numerous ways, one being the power of authority, right? So if the authority figures are kind of speaking this paradigm and people are buying into it, that, people aren't going to go against authority for many and various reasons. So that keeps paradigms in place. We also have the human experience. We're imperfect. So you're going to have, people are irrational sometimes. We are emotionally attached to certain ideas. We also have, denialism when it comes with coping with cognitive dissonance. And then we also, have this taboo, stigma, and ridicule that comes with ideas that are outside of these paradigms. So I think two examples that, we've seen in what I might say is recent history are like heliocentrism and germ theory. So heliocentrism is the idea that the sun is at the center of the universe. Or sorry, not the universe, the solar system. The sun is at the center of the solar system. And this was not agreed upon for, a long time. They thought, the Earth was the center of everything and everything was rotated around us. But actually, this is where the Galileo Project got our name from. Galileo used his telescope to make observations to find direct evidence that was disproving this idea that the Earth was at the center of the solar system.
This paradigm.
Yeah, exactly. So people refused to look through his telescope because they were either freaked out. Authority figures were like, well, we don't want to deal with the aftermath, of a paradigm shift because, people, who knows what that's going to do? It's
disrupt the status quo.
Yes, exactly. Disrupt the status quo. So people refused to look through his telescope. And then eventually, more and more people just came out with this and they're like, guys, this just doesn't make sense. So they're like, okay, we're going to throw that whole Earth-centric theory out. And now we've adopted heliocentrism. And now, people in our age, oh yeah, sun's the center of the solar system. We'd never doubt it. And that just had to come along with time. And then germ theory, which I don't know too much about. I'm not in the medical field, but I think it's the idea that certain diseases are caused by like microorganisms invading the body. So that was something that wasn't, necessarily agreed upon.
It was
controversial, yeah. So it's like you don't get scarlet letter stamped with a disease. It's like, oh, there are actually things that can like just make you sick. And then you can pass it to one another and that way. So it's funny to think about those things and like, oh, that's so insane. So I think, dare I say, we may be on the verge of something, whether it comes to, dark matter, dark energy, quantum mechanics, all of that. There might be a paradigm shift that's going to happen with that. But even UAP, I think to answer your question, that is why it hasn't received this scientific attention, is because it's scary. People are scared of it.
It is, yeah. And I think it also, even perhaps more so than heliocentricity, directly attacks our kind of high status as, our only inhabitants of this universe in a sense, right? It directly challenges our place there. Our heliocentricity, wait, that's the right word?
Yeah. Heliocentrism or whatever.
Yeah. Heliocentrism redefines our place in the universe, but this really defines our, our position of ourselves within the universe.
Exactly.
And that can be scary. Can be scary. Do you think science can overcome that just with data, or do you think there's going to be other, sociological, I don't even know what the right word is, tools or, things that we need to do to move people past this barrier? Or is it truly, do you think, just about data and communication?
Yeah, I mean, I don't think that you can kind of have one of those things without the other. So your science is nothing if you can't communicate it. So, and that goes for all sciences.
Do you think that's gonna be enough though for some people to see the data?
I don't think so. I really don't think so, which is unfortunate. I mean, me as a scientist, I'm like, yeah, show me the data. Like, that's good for me. But I know not everyone's like that. Some people, I think, if you don't have a sighting story, you might not be within the UAP community. Might be like, oh, well, you haven't seen it. You're not really one of us. I haven't experienced that, but I can imagine that might be the kind of mentality that some people have with it. Again, I haven't experienced that, so I can't say for sure. But I do think, that's why the Galileo Project, we have a societal implications group. And, those are philosophers, social scientists who are just really thinking about, once we publish papers and are getting data, how are we going to communicate that? And how is that going to impact, society as a whole?
Oh, that sounds fascinating.
Yeah.
When do you guys have papers coming out in that direction?
I'm not sure, actually. I think we have two papers that are kind of, higher level, and I'm hoping I've read them. I think they're, people can engage with them. You don't have to have necessarily like a rigorous scientific background. But one of them is about, just an overview of the project. And then that one's written by Dr. Avi Loeb. And then there's another paper written by Dr. Wes Waters at Wellesley College that is just giving kind of the history of UAP studies and outlining our approach as well and how we fit into that.
Awesome. Very interesting. Yeah. So speaking of how you fit in, what about yourself? So what is specifically you're doing to help the Galileo Project now? What is your title within that effort?
Yeah. So I talked a little bit about kind of the two other branches, but the one that's most relevant to this podcast is the UAP branch. So that's definitely, where I spend most of my time now. So within that effort, I'm working on instrumentation. So I'm on the ground building things, troubleshooting hardware, debugging, all of that fun stuff. And I started that 4 days after graduating, actually, from undergrad at Wellesley.
Wow.
Just went right into it. And I started off just as like a summer research fellow. So my time was supposed to be 50% with Wellesley and 50% with Harvard. I should also mention that Wellesley has a smaller subgroup within the Galileo Project related. They call themselves Celeste, which is Galileo's daughter's name, which makes sense. So they have a smaller group working there as well, because within this UAP, goal, we have an observatory class system. That's, what I work with now. That's about on the scale of $250,000. And then we have, one level below that, order of magnitude below that. And that's what Wellesley is working on. So they're, aiming for about $25,000, kind of like a rack mount. I should mention, sorry, I should say. So you have the observatory class system, about $250,000. That's, what I work with most. And then we also have Wellesley system, which is a level below that. That's $25,000. It's a non-weatherized system, but it gives you, enough things that, we still have some IR cameras, we have a microphone. It's just maybe not as expensive as, the highest level. Mm-hmm. And then below that, we have like a rack mount system, and that we're aiming for about like $2,500. So that's kind of like our three-tiered approach, because, we can't expect to everyone to have, I have $250,000 to give. Let me just have this observatory class system on my roof.
Mm-hmm.
Not everyone has a roof that, has something that big. So, we kind of make these different levels so that we can engage in the best way possible, especially, if there's an area where, sightings start to pop up, we can bring the rack mount system or the Wellesley system that's non-weatherized and just kind of set it up temporarily and just get some data. So that's kind of the reasoning behind those three. But yeah, just working on instrumentation and supporting the group. So I don't really have a fancy name. I'm just a research fellow. But
what kind of instruments are on, let's say, maybe the largest one there? I assume that has the most sensors. I could be wrong. But
yeah, exactly. It has the most sensors.
What are you looking for?
Yeah, I feel like we're just casting a wide net because we don't really know what to look for. Mm-hmm. So we're trying to cover all bases. So let's see if I can list all of them. So we have an audio system that's recording, audible range, but also infrasound and ultrasound range. Then we have an infrared camera system, and that's made up. It kind of looks like it's called the Dalek. We call it Dalek. Kind of maybe looks like R2D2. You'll see pictures in the papers, and they're probably, if you go on the Galileo Project website, you can see videos of our instrumentation, or some of it at least. So that's one that's on there, and that is made up of some boson cameras and infrared around the base, and then one on the top that's looking, at the zenith kind of area location, which is like right above overhead. And
What's
then
a boson detector?
Oh, it's a type of camera.
Got it.
Yeah. It's like a company, I think.
Very good.
So then we also have a visible camera. So that's like if you sat with your eyes and looked up the sky, but in higher resolution. I'm kind of blind, so I would not see as well as this camera would. But that's like 4K resolution. And then we also have a tracking camera. So those are going to talk to each other. So that tracking camera is actually it's a security camera. But, we're using it for not security purposes. So it just
security.
Goes... Exactly. Yeah, exactly. So if the infrared cameras see something interesting, if our AI algorithms, say, okay, hey, this thing is weird. Again, that whole question of how do you determine what is weird comes up again. That's something we have to revisit and talk about a lot. Mm-hmm. Then the camera is going to track, point to it, and then zoom in and try to get higher resolution than maybe our infrared cameras would. Let's see, what else? We have a spectrum analyzer. We have a magnetometer. We also have, we're working on a passive radar solution because we can't have the beautiful radar that you guys have. And the reason we're trying to do that passively is so that we can more easily set up our system and not influence, areas around us. It's hard if you're emitting radio signals. It's very hard to get approval and everything for that.
Yeah, limits your ability.
Yeah, exactly. So if you're passive, you're just sitting there. So it's that technology is really cool, but it's still developing. So very early stages of that. But I think, we also have a weather station. That's really important because you need to monitor atmospheric conditions because we don't know these phenomena could also be, related to weather as well. So I think we're just trying to do everything, making no assumptions about what's already out there, which it's pretty hard because usually the way science is done is that you maybe have a hypothesis or some kind of ideas that are, maybe gently guiding you to a solution. You're like, okay, well, I know I have to work within this framework or try to answer these questions. But we don't really have anything to go off of, at least from a scientific point. A big thing was, do we take into account people like witness accounts? Is that something we can use scientifically to justify why we're going to this place or why we have this instrument or that instrument? So it gets kind of sticky. It's hard to do it because then it's like you don't want to ignore the witness accounts either. But trying to set the standard for what the scientific approach for UAP is not something that's super trivial. So I think just casting a wide net, letting the data speak for itself, and telling us what's interesting and what's not interesting. That's interesting too. Is like if the audio and cameras are going off crazy and again, what is crazy, I don't know. But if for some reason they're finding signatures that are just bizarre, but we go over maybe to our passive radar, the magnetometer, and things look, sound as can be, that's also interesting because, we might have some kind of phenomena there as well. So that's my long answer to your question.
Does science work like that in other fields or in other examples?
I don't know if I know. I guess thinking about like computer science, I think with AI, the whole point of AI is to, not have humans make assumptions, but have the computer kind of make them. And that's definitely what we're relying on in our systems to determine like what is weird. It's like, well, we humans shouldn't be involved in that. We're heavily biased. But computer systems, they do a better job at clustering things and grouping things and just determining outliers. So I would say, in statistics, of course, you always are looking at data sets and determining outliers. So in that sense, I think maybe it's similar, but the whole approach of, having to, if you only have witness accounts, I can't really think of any other science maybe where it's like that, but there's probably something.
I wonder if you could, if you had a large enough data set, perhaps pull out some data using machine learning that was consistent across all the cases that otherwise might not be detected.
Yeah.
Do you think that's happening, or is that happening? Do you know if that's happening in the wider astronomy field for signal detection within the data sets that we're receiving, I'll say, from further away?
Yeah, I don't know. I think that'd be a question. I wish I knew more about like the SETI Institute, for instance, because I know like they're looking at technosignatures, and I'm sure they have things that they're using to determine if something is worth looking into more. But yeah, I don't really know enough to speak about it.
One of the reasons I ask you that is because I think I've read some articles about that, and of course, the further away you get from Earth, it seems, or from us, the more comfortable we are looking for life elsewhere, the more scientifically acceptable it is. Why do you think that is?
I don't know. I would love to read those papers if you remember what they are. I don't think I've come across them, but
yeah.
Yeah, I mean, I think like the universe is really big, so sometimes we have to look really far to try to see other systems that are like ours. But yeah, it is interesting because the way kind of like light works. So when you're looking farther away, you're also looking further back into time, because for non-science people listening or watching, light has to travel. So if you're looking farther away, that means that the light is going to take more time to get to you. So as you look further and further away, you're like seeing that light. Well, when the light reaches you, there's some time that had to pass when it was being sent. So it's like, I think you see this in a lot of James Webb, imagery. You see like really red galaxies. So that's something called a redshift. So the universe is also expanding. So when that light is traveling universe is expanding, it's shifting to redder wavelengths, which are longer wavelengths, and because it has to cover more space. So it's that whole play of space and time. But yeah, I forget your original question.
It's okay. I do that all the time. But really, we have the SETI, and SETI looks out and looks for distant radio waves, and maybe that just feels safer to us to think that we can look out there, and if we find something, it's not immediately threatening.
Yeah, okay, I think I understand your question.
Look at Mars, and it's like maybe there's microbes there, right? And that's not very threatening.
Yeah.
But then when we consider if there's something in our sky that theoretically could potentially be from elsewhere, that's a much more scary thought. So
yeah, and also it's scary to think about if there's, or at least I would say it's scary. I don't know if everyone else would. Maybe they think it's cool. That there's other civilizations that are more technologically advanced than we are. I think that also, is playing into that whole idea of, again, like paradigms. If you are seeing signatures, maybe, but I guess signatures can be threatening. Words hurt too. But it's like, do they speak the same language? Like, probably not. Like, how do they communicate? So, but yeah, no, I do think it's just like, again, it's also been hard because everything that, like your detectors and everything that you have used or seen with, other fighter pilots, that's all like classified. And we're getting kind of these bits from, the government reports that are coming out, but it's not enough for us to like actually scientifically evaluate, the situation. So we kind of have to take our own data to figure that part out.
And, I know that leads to people's ability to kind of push back and say this is silliness or nonsense, or try to, discourage you perhaps from engaging in this field. So, as you were considering kind of engaging in the Galileo Project, I mean, you said you didn't really necessarily know what you're getting into, but now here you are, on my podcast talking about it.
Yeah.
So, what has been, you made a decision to kind of lean into this a bit. Did anyone have any conversations with you and discuss, potentially what the implications of that could be, or was there any pushback? What are your experiences kind of diving into this?
Yeah, no, I think that's something I'd love to talk about, because I'm sure now, as more people are coming into this field, it's something they may be thinking about or considering, as reasons for them not to get involved. I don't think I ever received any like official warnings or, anything, but it was just kind of unspoken. Like, okay, I guess I should say, so I was doing that independent study, and then that same, Professor Wes Waters asked, what I like to do with summer research with the Galileo Project, working on instrumentation, so switching branches, but still under the same umbrella. And, at that point I had, full intentions of applying to grad school that next year. So I was just thinking, I did think about it. I was thinking, okay, how is my involvement going to be received from people who are maybe viewing my application for grad school? And I definitely had to take a little bit of time to, think about that and, weigh pros and cons. Because I think it'd be silly to say like, oh, I don't care, it'll be fine. But if you kind of make this decision, you might be affected for your career. Or at least that's what I was telling myself. But eventually I was looking at the project, and, my experiences up until then had been no different than any other astronomy research experiences. Like the previous summer I was at Cornell working on instrumentation that's going to look at, it's like cosmology instrumentation. So the atmosphere didn't feel any different than that. So I was like, okay, well, as long as I can explain myself and, the things that I'm doing are very fundamental, they're scientific, I'm developing skills in hardware, coding, debugging, all of that, and that's going to be really helpful. So I just kind of thought, okay, it's going to be about framing moving forward, but also if I'm applying to these institutions and they're going to judge me for engaging in this topic, even though it's with the proper methodology or great methodology, that's probably not a place I want to be anyway. So I'll go ahead and let them filter themselves out, because I don't want to go to a place and be surrounded by people who are not encouraging of scientific processes. Because again, it's like nothing that we're doing is maybe different in terms of our science goals. We follow all the same processes that you would if you were working on another scientific project, because just the application is a little different. Yeah, the application is a little different, the target's different, but who cares?
Mm-hmm.
So that's kind of, I just was like, I'm going to lean into it. And, I've never received any pushback. We were speaking a little earlier. I applied to grad school. I've been admitted to, multiple places. So it seems like it's been well received. And I think that fear I had in my head was totally like self-fabricated.
Yeah.
And I think the people that maybe do think that way, maybe they just stay quiet, which, that's fine. But I really do think that over time, it's going to change a lot. I mean, just like talking about it to my friends and family, like they're all just so excited to hear about what's going on. And, I've been really able to bond with a lot of my family members. Like my grandfather or my great-grandfather worked on planes in World War II. Cool. I feel like in some ways I'm kind of, engaging with that side of my family. And, they've been interested in the topic for reasons, because I think it kind of started out in like a military kind of perspective. And it's cool that
what
science
started out with the military perspective?
Or the UAP kind of topic. Okay. It's like that's where they started having these, where they started kind of maybe collecting science or collecting data about these objects. Because before that, I think it had mostly been witness accounts. So that's kind of the first time where they were like, it's weird because our instruments said that they were kind of strange. So in some ways, like I'm talking to like my grandfather, who also, was a pilot. And I think like talking to him has been awesome. He's just fascinated by it.
Has he seen anything?
No. I wish I had stories, but no, I don't have any. But I think it's just the idea of it. And they're just really excited that, I think the other point I'll make is that I think one of the reasons that the Galileo Project has, gone to where it is now is because of that Harvard name that's attached to it. So I think that has helped give it credibility. Which, might not have had if it was another institution, unfortunately. Mm-hmm. So I definitely, when I was like telling people about my job, I would definitely lean into that first. Like, oh, I'm doing research at Harvard. And I'd be like, okay, maybe they'll ask what I'm doing. Oh, I'm doing instrumentation. Oh, instrumentation, yeah, for UAP. So I definitely like kind of I would approach that in layers for probably the first couple of weeks I was working. Mm-hmm. And then, like I said, I just decided, you know what, I think this is worth speaking about. And I kind of just gained confidence in that, in the mission. And I was like, okay, we're just going to lead with that. So anytime we're like out with, and I'm meeting new people or acquaintances, and I'm with people, for instance, like my roommates who know what I do, and, people come over, they're like, oh yeah, what do you do for work? And we all just kind of look at each other and smile, because we know that my answer is going to kind of blow their mind. So I've just like leaned into that, and it's become like really fun. And I think that's one of the ways we can, at least as young people, like bring this or help this discussion, is to just talk about it more and, do it in a sense that isn't talking about sci-fi movies, but actually talking about like, people's jobs and how they're engaging with it.
And the science.
Yeah.
It's incredible. Are you seeing that your friends are much more open to the topic?
Yeah. And I think, again, that kind of plays into like with time, I think it'll change. But yeah, I haven't ever, to my face at least, received any pushback from friends. It's all been like genuine interest.
Mm-hmm. That's very cool.
Yeah.
So where is the Galileo Project today? They're building sensors. You're building sensors. You have a couple different types. You have a big expensive one, and you're working to bring the cost down and make it more scalable. Have you guys started like making what I would call like production detections, or are you still kind of in a testing phase right now?
Yeah, so I would say, straight up, we're definitely in the testing phase right now, but that's the most important phase. So the terminology we've been using is we're in phase 1. So we have our first observatory system. We had it installed on top of the Harvard College observatory roof for a while. We were just, testing that everything, like the hardware is behaving as we're expecting. And then we were able to move to another instrument site, which I'm not allowed to say where.
It's classified.
Classified. But that is where we can, do a little bit more rigorous testing. But yeah, so definitely just like making sure things are running. Sometimes you need to go out there and unplug some USB cables and replugging them in. So we have to troubleshoot, like, why did that happen? and thinking about, what that says in terms of our technology capability, how hands-off is it, how hands-on is it. So just determining all those things is really important in this phase one. But also, we have a science traceability matrix that says all of our goals, areas where we want to make sure these instruments are performing up to their specifications. So just referring back to that always, which that'll be in our papers that are coming out. But just referring back to that and making sure, okay, we said we wanted to get this resolution of objects. We want to be able to see objects moving like this fast or this far away. Just making sure that we're actually seeing that. So,
and you define all those parameters in some of your upcoming papers?
Exactly. So those are very, they're detailed and they're lined out just like they would for any other, scientific project. So I think that is really important. So we've kind of put a pause, or not put a pause. We've just kind of taken this opportunity to, now that things are kind of going, to make sure we're doing the preliminary analysis and, again, performing up to spec. So that involves a lot of observing birds and planes for right now. But, we have the cameras rolling, so if anything decides to give us a visit, I guess we'll have it. But it's just, like we were kind of speaking about a little bit, how you determine that something is weird or anomalous. We're going to let the AI algorithms handle that for us.
Got it.
So in order for those, algorithms to operate, they need to collect large amounts of data first. So they need to see a ton of planes and a ton of birds and a ton of insects, and so that they can cluster them together in groups. And then once that clustering starts to happen, you can kind of see, okay, maybe there's a couple of points that are just hanging out over here. Let's go and see what those are about. And then that's where, we'd maybe start to go into what we would say like anomaly detection. So it'll be definitely like a continuous process, but I would say we're definitely in like the testing phase right now. But taking all this into consideration, and we're hoping soon. I think our goal right now is by August, where we've kind of started the introductory papers outlining like the hardware of the system, and the goal is last year to kind of have our first round of papers about like data and our interpretation and methodologies there. So definitely stay tuned for that. But
that's in 2024, the fall?
Yeah, so I guess depends on what journals we submit to and what their processes are like for feedback, and then how long they take to publish. But I would say hopefully, so it'll be like a batch paper will come out, and then a year later they'll be supplemented with more.
Got it.
So yeah.
So the papers I don't think are necessarily part of phase one, but that kind of validation and testing that you talked about is phase one. Is phase two more of just kind of the data collection and waiting to catch something, or is that what phase two would be?
Yeah, so I should clarify. I guess phase one is more, the phases is more in reference to like what hardware we're using. So phase one includes like the whole process of designing and whatever. So all of our papers that are coming out are about our phase one instrumentation.
Got it.
So it's outlining, hardware, what we're using, all that. So that, the whole point of this, and for, good science studies, you want to make sure that your studies are able to be replicated. So we want to outline all the details so that if someone, another group or another university would pick up our paper, follow everything exactly, they would hope to get, the same results that we're getting. That's the whole point of these papers, is to outline, what we're doing, being transparent about it as much as we can. And yeah, so that's kind of phase one. And then we're kind of thinking about, okay, like phase 1.5, maybe we replace. So for instance, one thing we're talking about now is we have this Dalek camera, which I was talking about earlier, which is made up of infrared cameras. Is it better to have one big one or two smaller ones spaced apart? So things like that, you just have to test and kind of see what happens. And you can, calculate theory and everything all day, but it really comes down to, when you're out there, what are you getting, and what can you do? So, just making sure our pipelines are running smoothly, and that the hardware is behaving as expected is the highlight of phase one. But for phase two, that's adding a couple instruments. So I guess I spoke excitedly. The magnetometer isn't technically part of our phase one yet, but it's something I work on. So it's in the works. So it's almost like phase 1.5. It's almost like in the middle, but like that. And then we're adding a spectrometer. So it's just a couple of things that are a little bit further ahead. So that's like kind of phase two will be like an upgrade to our systems, or thinking about, again, technology is always improving. I'm talking about those infrared cameras. Well, that same company just came out with a plus version. It's more expensive, but it has better resolution and all this. So it's like, okay, well, where do our limits lie? Do we need something that's better? Do we not need something that's better? So it's just a lot of those like little questions that we're trying to answer right now.
So things are progressing as expected.
Yeah.
People shouldn't be waiting for some massive announcement tomorrow or anything.
Yeah,
crazy,
exactly. No, it'll take a while to get there, just like I said, because, we are trying to do this very rigorously and scientifically. So even if we see something that doesn't quite make sense, we're going to wait for our AI algorithm to tell us that, not just with our eyes.
Wait for the scientific process.
Yeah, exactly. And making sure, we're referencing all the other instruments. Like we saw like a bird fly by that was like in a weird trajectory, and we were like, oh, that's so cool and exciting. But it's like, oh yeah, we can see it's a bird. We can hear it's a bird. So it humbles you very much.
Yeah.
And separating that, I think, not everyone on the team is believing in the same outcome, right? There are some, like, I guess you would say, like, non-believers, which I think is important to have on a project like this to make sure you're doing it right and you're incorporating everyone's opinions and viewpoints into the approach and discussion. But I guess I would say I just hope that, I can't say what I hope that we find because I don't know, but I just hope that this sets a standard that you can do science that is looking into phenomena, whatever that phenomena may be.
Awesome. Well, I'm really happy you're looking into it and taking an interest in it.
Thanks. Yeah, thank you for, bringing this to light. And obviously would have never happened without, the bravery of many people who have had experiences and witness accounts coming forward and really fighting for this to get the attention I think it deserves. So
awesome. Well, we'll be watching, and good luck.
Yay. Thank you.